The next topic is quantization of input data. When we process an analog signal using a digital system, the analog signal has to be digitized using a analog to digital converter. So this ADC will consist of two parts, that's a sampler as well as a quantizer. The sampler will sample the value of the analog signal at a uniform intervals to produce an unquantized signal. The quantizer will quantize the analog value and produce the corresponding binary codes. The two types of errors are produced by ADC process, that are quantization errors and saturation errors. Quantization errors are due to the representation of the sampled signal by a fixed number of digital levels. The saturation error occurs when the analog signal exceeds the dynamic range of ADC. So, if I am having two, consider I am having two quantized level. Quantized level. This is one of the quantized level, and the another is this one. If I am having a signal, analog signal, like this, and if I sample at this interval, it is either quantized to this value or quantized to this value according to the nearest level. So if we consider a point at the center of this, so the maximum quantization error in the positive side is q by 2, or the negative side it is minus q by 2 if the q is the step size of the quantization ladder. So the expected value of the error signal, if error signal is denoted by E, error signal, and the quantization value is this is the one mistake. Yeah. This is minus q by 2 minus q by 2 and plus q by 2. So the amplitude of this will be 1 upon minus q by 2. Amplitude of the value is 1 upon 1 upon q by 2 minus q by 2, that's equal to 1 divided by q by 2 plus q by 2, that's equal to 1 by q. So this amplitude is 1 by q. Simple. So the expected value of error signal value of error signal is E of is equal to 1 by q into integral minus q by 2 to q by 2 e into d. There is the error. So this is 1 by q into integral minus q by, sorry, when we integrate this, e square divided by 2, that is equal to uh, minus q by 2 by 2. So 1 by 2q into q square by 2 minus q by 2 the whole square, that's equal to 1 by 2q into q square by 4 minus q square by 4, that's equal to 0. So variance of the error signal, variance of the error signal denoted by sigma e square is equal to expectation of e square, that's equal to, sorry, expectation of e square minus expectation of e square. So that's equal to, since the value, expectation value of the this value is 0, sigma e square can be denoted as expectation of e square. So that's equal to sigma e square is equal to 1 by q integral minus q by 2 to plus q by 2 e square into d, that's equal to 1 by q 1 by q into e cube by 3 minus q by 2 to q by 2. So this is equal to 1 by 3q into q by 2 the whole square minus q by 2, sorry, whole cube minus q by 2 the whole, that's equal to 1 by 3q into q cube by 8 minus q cube by 8, that's equal to 1 by 3q into 2q cube divided by 8. So 1q is cancelled and q square becomes here. This is 4. So the variance sigma e square is equal to q square by 12. Next we have to find the steady state output noise, the steady state state output noise variance due to quantization. So let the quantized input of the digital signal can be represented as the sum of unquantized signal x of n with the error signal. So xq of n, which is the quantized signal, is equal to x of n plus the error signal e of n. Since we take the output, y dash of n can be represented as xq of n convolved with the my filter function h of n. So this can be represented as x of n plus e of n convolved with the h of n. So this is equal to x of n convolved with the h of n plus error signal convolved with the h of n. This is equal to y of n plus some epsilon of n. So the steady state output noise power, steady state output noise power due to quantization can be represented as sigma e output noise power, sigma eoi square is equal to sigma e square, into summation n is equal to 0 to infinite h of n square. So sigma e square into taking h of n square as 1 by 2 pi j, which is the inverse of the Z transform, over c h of z into h of z raised to minus 1 z raised to minus 1 dz using Parseval's theorem. So the sigma e o I square is equal to sigma e square into summation I is equal to 1 to n residue of h of z into h of z raised to minus 1 into z raised to minus 1 dz. Sorry, there is not z because there is no intent. And z at the term z equal to p. So sigma eoi square can be represented as as sigma e square into summation I is equal to 1 to n z minus pi into h of z, h of z, h of z raised to minus 1 into z raised to minus 1 will equal to, where pi is can be represented as p1, p2, p3, etc. up to pn, which are the poles of h of z, h of z raised to minus 1 into z raised to minus 1. Since the closed contour integration in the equation is around the unit circle, that is mod z is equal to 1, only the residues for the poles lying inside the unit circle has to be considered. This derivation can also be used in the case of the output signal.